Hello, everyone, and welcome back to the 2021 Cementing Leaders Forum. I'm your host or moderator, Jordan Trosclair, Global Sales Manager for Cementing. If you missed our sessions yesterday, in the morning we covered Halliburton 4.0, the IDOS well program, and the virtual remote operations. The 11 a.m. session, we covered sustainability, cross-training in the cementing PSL, and the North American Land Manual Calculator. We've had really good questions coming in and very good participation, and we really appreciate everyone's time for calling in today and yesterday. Please remember that we have a live Q&A at the end of the session, so post your questions at any time during the presentations, and we'll get to answering them at the end. And we're going to go ahead and get started with our very first presentation on iCem 7.0, and we'll start with Krishna.
Good morning, everyone. Welcome to day 2 of CLF 2021. This is Krishna Irubandi. I'm one of the advisors with Cementing PSL. Today, I'll be talking about iCem 7.0, all that is latest and greatest in cement job design modeling. Yesterday, we talked about Halliburton 4.0 and then also about well construction 4.0, which is part of the Halliburton 4.0 initiative. This slide explains 2 tenets of well construction 4.0. One of them is the digital well program, and you will see signs or the job design models that we use are an integral piece of the digital well program. And also for the other tenet, which is digital well operations, we are talking about real-time data acquisition, real-time data streaming, and those are also key components that will come from iCem itself. iCem is already an industry leader with its state-of-the-art displacement models, hydraulics models, and real-time data acquisition. And with iCem 7.0, we are taking that to the next level. Getting into the details of what we have new for iCem 7.0, we have introduced a lift pressure calculator. It's a rapid pressure matching tool, and we'll get into the details. Real-time and recalc hydraulics has been improved. That is for detailed pressure matching and post-job analysis. We have introduced a stiff string model for standoff and centralization calculations in the previous versions of iCem. And with this version, we are bringing that capability for torque and drag calculations as well. We have improved the 3D displacement model for reverse circulation cementing and also for balance plug pumping. For those of you who understand or who have seen Compat tool from Halliburton, that is integrated with the iCem 7.0 now. And we have also incorporated casing equipment catalog or library selection within iCem itself directly. Cement dependability index is improved with new additions on the front end for the users, and also the way we collect this information for accumulation in our wide-up platform has also seen some changes, and we'll go into the details. And there are a few more updates and upgrades that I'll be talking about. Getting into the details, lift pressure and or the TOC correlation calculator, it's a rapid pressure matching tool. So you start with a pump schedule that is representative of the real-time job itself, and we don't need to be detailed, but at least it should represent the aggregate behavior. And once you have that, and also once you have a recorded pumping pressure or the lift pressure that you would like to match, iCem would do the the hard work of going through hydraulic simulations, iterations, and finally recommend an open hole access that would give you the lift pressure, or in cases where you have losses, it can also recommend the location of the loss itself. It will return a full iCem job for you to run additional calculations like 3D displacement, and so on and so forth. Here is an example of how the lift pressure calculation works. It's a very simplistic case. You have a 2000 feet well, and then cement is supposed to be coming to the top, 0 feet. And once you run the design calculations in iCem, you'll see that it is recommending, it's suggesting that you will receive around 900 psi lift pressure. But for whatever reason, if you have observed that the job itself went up to only 600 psi for the final pressure, and you can bring that to iCem, and of course, after updating your pump schedule to reflect what has been pumped during real-time rates, volumes, and densities. And iCem would iterate through various hydraulic simulation iterations, and then recommends an open hole access, and then finally some results associated with it. In this case, it is saying that the cement volume that you have pumped is not reaching all the way to the top because of the open hole access that should give you the surface pressure of 600 psi, and it is only reaching up to 560 odd feet. When you run design calculations, you get away with larger volume increments or the time steps to understand the transient behavior of the ECDs or the pumping pressure values. And the reality is never that smooth. You won't be pumping density at really close to the design density. It'll fluctuate a little bit depending on the mixing system, and you won't probably be maintaining the flow rate as smooth as you would like, and so on and so forth. And then these deviations from the design itself can bring in significant deviations on the calculated ECD values. And the only way you would understand that impact is if you can run the calculations at the frequency of the real-time data itself. And that's where a real-time recalc hydraulics will come in. It will let you calculate the bottom hole ECDs or the ECDs at different locations, plus the calculated surface pressure or the surface pressure value second by second, which is basically the frequency at which we typically record the data. When you want to do this post job, you would use the recalc feature within iCem. For an example, on the chart you have in the yellow color the recorded pressure, and then the red one is the density at which you have pumped the job, and then rate at which you pump the job is in the green color. Now you will be technically able to feed this data through our hydraulics calculations and generate some predictions which are at the same frequency as that of the real-time recording itself. So in this case, you are seeing a new curve which is in blue. Is the calculated pumping pressure value. This is the pressure at the pump. At the same frequency, it is calculated at the same frequency as the real-time data itself, and you can see all the wiggles and whatnot that are strongly correlated with fluctuations in the data itself. One observation I am drawing your attention to is during the displacement phase. The calculated pumping pressure value is indicating that it should grow, it should build, but the real-time data is indicating it did not do that, and it could potentially be a case of losses getting induced at that point during the job. Moving on to stiff string calculations. Stiff string is the name that we use when we represent the casing or the tubing of the well bore with its stiffness influencing the forces in the model. And the forces we are talking about are either on the well bore, on the casing itself, or maybe any loads on the RKB or the hook itself, right? So we have incorporated this kind of models for standoff calculations, which is built on FEA, and we are bringing that for torque and drag models now. The results of the torque and drag model are an estimation of the load on the hook as the casing is moving down in the well bore, and we call that casing shoe location in the charts. You have the ability to select between soft and stiff string models, the way we have done it for the standoff calculations. And one observation or one note for anyone who is using stiff string models and then comparing them to soft string models is for wells with high build rate or high rapid change in the well profile, especially the deviation, you would see a difference between soft string and then stiff string estimation of any forces that you're calculating. And I'll show you that with the charts that are generated for the case that I'm showing here. On the left-hand side, you have the soft string models, and on the right-hand side, we have the results from the stiff string model. And as you see, the soft string model stays more or less smooth, irrespective, and there is an inflection which is indicating the directional change itself. But the stiff string model brings in some characters, the effect of the stiffness, which is basically making it difficult for you to navigate through that 90-degree bend in all the three charts. And one observation is the aggregate forces, like especially at the static weight, they are in the same ballpark, very close by, which is indicating that on an average, the behavior is same. It's just that the stiff string model is bringing a little bit more character to the plots. Moving on to the displacement calculations, we have enhanced the model to support for the reverse circulation cementing. And it will support every combination of the well that we can possibly create in iCem at this point of time, which includes ERD wells, vertical wells, inclined wells. It'll bring in the effects of fluid friction, rheologies, and the density differences. We are calling this for reverse circulation cementing, but we can technically use this functionality for any scenario where we are pumping the fluids in the annulus top down, including bullheading and squeeze jobs. Here is a sample results that we have recorded for a reverse cementing circulation job. For those of you who haven't seen 3D displacement results, this is various color contours we generate for the job. And these are same for primary cementing, or the forward cementing or the reverse cementing. As you can see, the fluids are flowing through the annulus top down. We are able to see that in the unrolled view, how those fluids are moving. And we are generating results or the fluid concentrations across the well bore and as a function of time as well. And also we have the standard result of predictive bond log, which is concentrations at the end of the job along the depth of the well bore. Moving on. For the balance plug pumping scenario, we are one note, we are not doing the fluid contamination when we pull out of the pipe. This is only the analysis done during the pumping of the balance plug. This is a feature that is requested by couple of our customers and then our engineers, they are having to convert the balance plug jobs to forward cementing jobs to do this kind of analysis, and then we just remove that restriction so that they can do this kind of analysis directly with the case that is created for the balance plug. A brief description of how compare tool functions. With compare tool, first of all, we'll calculate a representative RPM for the wellbore conditions. So at a given flow rate in a given geometry, you will have an average shear rate that is defining the fluid movement characteristics, and we can convert that to an equivalent RPM for the typical viscometer that we are using. And once you have that, you want to look at how different concentrations of the fluids are behaving, and that's what these charts are. Because you can't directly get the dial readings at the RPM of interest, what iCem does is it will look for the RPM slightly above and also the below the representative RPM on the charts there. The red chart is talking about 30 RPM, just which is below the representative of RPM of the wellbore, and then green chart is above the representative RPM of the wellbore. And the solid line is the ideal behavior, which is coming from the linear mixing rule. And what we are doing here is to look at the compatibility results in comparison with that of the solid line. And general rule of thumb is we really don't want the dots go above the solid line, and if they are going above, it should not be more than 20% for the sake of restricting unrealistic or unmanageable pressures in the wellbore. Casing equipment catalog of Halliburton casing equipment catalog is directly integrated with iCem. Right now, we'll be able to look for the stock and then search for different casing equipment based on the region and then the material identification number, and also some features of the material itself. For float shoe, you'll be able to filter them by casing size and casing weight, and then if it is something else, then you will have other filters showing up. And once you add this equipment to iCem, iCem will automatically pull the specifications for this equipment, and then it will add that to the report for general consumption. Now, this is the first version of this feature, and in the future, we have plans to enhance this by bringing in smart recommendations. So iCem recommending certain kind of equipment based on the job profile, and also some warnings and validation just to make sure that we are not using an equipment that is not suitable for the conditions and then specifications of the wellbore under discussion. CDI has been introduced a few releases back, and with this release, there are a couple of changes. We are adding 2 more questions for the evaluation, and we are changing the way we are tracking the responses for these questions in our centralized repository, VIDA. Future versions of VIDA will have features where it will score the job based on the answers to these questions, and also provide recommendations on what could possibly improve the success of this job in terms of the CDI responses. Other upgrades or additions, we have introduced Particle Wizard tool in iCem 6.0, and with this version, we are expanding the list of materials for it and also updating some of the concentration limits for the existing materials. Landstreamer is a way of sharing the real-time variables, real-time recorded variables or calculated variables in a local network wirelessly, and you should be able to stream the data to something like a mobile phone. In this case, we are showing a screenshot of the mobile phone, or some sort of a tablet or a laptop as well. And that feature has seen improvements with this release. We have expanded the list of variables or number of variables that we can support up to 10. iCem static object is updated to the latest standard. Those of you who are using iCem static object for getting the valve packet or the design and then real-time reports, this is updated to the latest standard, and then it should work seamlessly for your use case. With that, we come to a point where we can discuss a little bit about the future releases, and the development of iCem itself doesn't stop with 7.0. And in general, we take a multi-generational approach to any features that we are building. I briefly talked about something like the smart casing equipment recommendations feature, and that is going to be built on whatever work we have done for 7.0. Similarly, for the 3D displacement, we are heavily investing in improving the performance of the 3D calculations, most often requested feature or improvement from our customers. And also we are looking at ways in which we can bring the 3D displacement close to the ground reality, which is the bond logs. So something that we are looking into. And on the real-time hydraulics or the hydraulics front, we are envisioning a feature, we are calling it real-time advisor, at least for the first version, is to bring in advanced analytics on the real-time data that we are recording, and either through the help of the hydraulic calculations or something that is on the data itself. Couple of improvements on the models itself. We are looking at opportunities where we can update our erodibility calculations based on our recent findings, and then also potentially bring those changes to 3D displacement, along with the losses. Liner top crossover tool, support for liner top crossover tool is something that's been on our list, and we are looking for some feedback either through this session or elsewhere on where that feature would sit on your priorities. One final note here, and you would observe at least one significant trend in these features, and we are looking at various ways in which we can bring our models really close to the data, whether it is log comparison or real-time enhancements, but something that is we are really interested in doing. And in the subsequent rapid fire sessions, we'll be demonstrating case studies that'll compare the models that are there in iCem with the real-time recorded data. With that, I would like to thank you all for tuning in, and I'll hand it over to Paul Osborne for the rapid fire session.
Hey, good morning. My name is Paul Osborne. I'm the North America Land Region Technology Manager. And the case history I'll talk about today is utilizing iCem 3D, as well as some samples that we collected during the job to overall evaluate the effectiveness of our surfactant package, as well as spacer volumes. Okay, so just to frame it up a little bit, this particular well bore, it's an 8 3/4 inch open hole with a 5.5 inch casing. The average measured depth was around 18,000 foot, and the lateral length was about 2 miles or so. So historically, the customer liked to determine the spacer volume, determined from or calculated the linear footage from the cement top up to surface. The customer wanted to change their cement top to a shallower depth, which thereby was going to reduce the overall spacer volume. So the question came up, what's going to happen with our overall cement job and the performance of the spacer if we reduce the spacer volume from 120 barrels down to 80 barrels? So what our solution was first of all, we wanted to collect samples. So what you see here in the pictures in the upper left-hand corner, that is pure mud. So that was collected while we were doing pre-job circulation with the rig pumps. In the bottom right-hand corner, that is pure spacer. That pure spacer was caught off of the mixing truck as we were mixing on the fly. The other samples that you see, that's the mud spacer interface. So we wanted to collect that mud spacer interface as it was coming to surface during the displacement of the cement job, right as we were landing the top plug. The second phase was to take all the samples that we collected and bring them back into our laboratory. So we wanted to run 4 different lab tests on those representative samples, really trying to understand what was the fluid properties as we were pumping into the wellbore, as well as the fluid properties of what was coming out of the wellbore. And so ultimately what we wanted to do is take the results, the rheology and compact testing specifically, plug that into iCem, and then run our 3D calculation. And overall, we wanted to do the comparison of what iCem 3D modeling tells us versus the actual physical measured values that we collected from those samples, mainly density. So here's the results. So we did 120 barrels of spacer. You can see that there was 12 minutes of contact time and about 3,000 feet of fill. We did achieve about 70 barrels of spacer to surface. When you look at the table, look at the second to left column, that's the measured density. So that is physically what we measured with all those samples, and compare that to the third or middle column, the iCem 3D calculated density. You can see that the density comparisons were very, very close, all within about 4%, which we feel like is a good overall model prediction. Additionally, on the far right, you can see the rod test results. So this is where we were trying to measure the surfactant's effectiveness and to see if it was going to be spent or not. As you can see, the first 50 barrels of the 120 barrels, the rod test failed. So what that ultimately tells us is that there's a lot of intermixing with spacer and mud, and the surfactant was doing its job for a certain portion of that spacer volume, and allows us to optimize either the surfactant package and or spacer volumes. Ultimate results here for the planned top of cement for this particular job was 1,000 feet. The cement bond log evaluated and determined that the top of cement was around the same depth, 1,170 foot. And our iCem 3D model, which gave us results of 80% displacement efficiency, which is our target goal of 1,951 feet. So with all these results coming combined together, we presented this back to the customer and ultimately determined that the 120 barrels of spacer, which was the volume that we were pumping prior to the change in top of cement, was going to be more than adequate to continue to pump. And there was greater risk of reducing down to 80 barrels of spacer based upon our 3D results. Hey, thank you for your time this morning. And now I'll hand it over to the next presenter, who's going to present the use of the particle wizard and how we optimize an LCM package to go through various casing restrictions. Thank you.
All right. Good morning, everyone. My name is Nitish Khanna. I'm a senior technical professional with Halliburton, currently supporting cementing operations in the Rockies area. I have been with the company for almost 5 years and worked in multiple locations across North America land. This morning, I'll be discussing a case history wherein we utilize the particle wizard risk assessment tool in iCem to design and validate loss circulation and well life material loadings for both spacer and cements. Now, LCM is typically added in spacer and cements to cure losses and achieve a desired top of cement. However, introducing LCM in fluids does pose certain risks in terms of plugging any restrictions in the wellbore, like valves or ports in casing equipment. Therefore, it is extremely important that we use a quantitative approach to minimize the risk and maximize the probability of eliminating or reducing losses. To give you some background, a customer in North America land was planning to set surface casing across multiple unconsolidated and low fracture gradient zones, where loss circulation is known to be a major concern. The client identified achieving cement returns to surface as the key measure of success. In order to meet this objective, Halliburton proposed the use of a tailored LCM package, which would help address a variety of loss circulation scenarios, ranging from seepage losses all the way to severe losses through fractures. The customer next challenged Halliburton to develop an aggressive approach in terms of LCM loadings, both in spacer and the lead cement, therefore improving the likelihood of of actually getting cement returns to surface. Now, this is where we used the Particle Wizard risk assessment tool to estimate the maximum LCM concentration that can be safely transported by the fluids through the smallest restriction in the wellbore and can be adequately suspended during any planned shutdowns. In the risk assessment, we evaluated 3 key performance criteria: particle transport efficiency, static suspendability, and safe passage. Now, only when all 3 performance criteria are met, the job is approved to be pumped. Particle transport efficiency is a measure of the fluid's ability to keep LCM suspended in a dynamic state, whereas particle static suspendability, as the name suggests, is the measure of the fluid's ability to keep LCM suspended in a static state. Both these are a function of fluid properties, LCM physical properties, and wellbore geometry. The particle safe passage, on the other hand, is a measure of the maximum LCM loading that can be pumped to the smallest restriction along the wellbore. Now, this is a function of the minimum flow area and the minimum clearance in the restriction through which the LCM-laden fluids have to be pumped. While performing the Particle Wizard risk assessment for the scenario on hand, it was identified that the 3.5-inch valve being used in the third-party float equipment was the limiting factor. The maximum allowable LCM concentration could just not be achieved due to increased risk of particle crowding across the valve opening. In order to overcome this, we proposed using Halliburton Super Seal 2 float equipment with a 4.25-inch valve. This valve has both a greater flow area and greater clearance, allowing for particle safe passage. By making this change in the float equipment, we would be allowed to use 50% more LCM in the Tune Defense cement spacer and 90% more LCM in the lead cement. Now, 10 jobs had already been completed successfully when using the lower LCM loading and the third-party float equipment. However, for the 2 wells in question here, where increased losses were expected, the customer decided to use the higher LCM loadings and the Super Seal 2 float equipment with the 4.25-inch valve. Both the jobs that we completed were successful, with cement returns being seen on surface. No abnormal pressure events were observed as the fluids passed through the float equipment, therefore validating the analysis. In conclusion, the Particle Wizard risk assessment tool in iCem is essential in designing and optimizing jobs that have low circulation as a major concern. It can set design limitations and help identify areas of improvement in slurry design, LCM selection, and float equipment selection, all with the aim to increase the probability of reducing or eliminating losses and achieving the desired top of cement. This tool provides us with a quantitative approach to manage the risk and reward of pumping low circulation and well life materials in different fluids. I would like to thank you very much for your time, and I now pass it on to the moderator, who can open the floor for questions.